Hi, in this video we're going to be exploring the relationship between the standard free energy change for a reaction and that reaction's equilibrium constant. And it turns out that if we know something about one of these two, we can determine something about the other. And it's important that we remember what these terms mean. So delta G naught prime is the standard free energy change for a reaction. That is, it is the sign of delta G under standard conditions, which is when products and reactants are continuously present at 1 molar. The equilibrium constant, remember this prime just tells us a neutral pH, the equilibrium constant is the ratio of product to reactant when the reaction is at equilibrium. And remember, a reaction will proceed spontaneously in the direction that moves it closer to equilibrium. So beginning with concentrations of products and reactants at any values, we can determine whether a reaction would be exergonic, negative delta G, or endergonic, positive delta G, by determining whether that reaction would be moving closer or further from equilibrium. And what we're going to see in this presentation is that if we know the sign of the standard free energy change, that is, if we know that delta G naught prime is positive, negative, or 0, we can determine whether the equilibrium constant is less than 1, greater than 1, or equal to 1. On the flip side, if we know that the equilibrium constant is less than 1, greater than 1, or equal to 1, we can determine unequivocally if the standard free energy change is positive, negative, or 0. And we're not going to do any calculations. We're just going to be comparing standard conditions to equilibrium conditions. So, suppose I told you for the reversible reaction X converted to Y, that the standard free energy change is plus 250 kcals per mole. Now, remember, the standard free energy change tells us that our concentration of X is 1 molar and Y is 1 molar. That's the definition of standard free energy change. And what we're being told is, if we're beginning with equal amounts X and Y, that the reaction, the forward reaction, is plus 250 kcals per mole. By the way, if forward or reverse is not specified, we always assume the forward reaction. So we're starting with 1 molar X, 1 molar Y. The conversion of a mole of X into Y requires an input of 250 kilocalories per mole. That is endergonic, input of energy, non-spontaneous. Now, based on this information alone, we can determine if the equilibrium constant, that is the ratio of Y to X when this reaction has reached equilibrium, is less than 1, equal to 1, or greater than 1. And here's one way that we can do this. So here we have plotted the free energy of our system on the y-axis and all possible ratios of product to reactant, Y to X. The system has the lowest free energy when it is at equilibrium. Now, one thing that might help you is to pick a point to the left of the equilibrium constant, to the right of the equilibrium constant, and determine what the sign of delta G would be moving forward or reverse at either of those points. So here we've picked a ratio of Y to X that is less than the equilibrium constant, and it has higher free energy than we would if we were at equilibrium. And hopefully you can see that beginning at this particular ratio of Y to X, the forward reaction is exergonic, negative delta G. Converting X into Y would release energy. The reverse reaction is endergonic. Moving away from equilibrium requires an input of energy. Now, if we come over here to the right of our equilibrium constant and pick a ratio of Y to X that is greater than KEQ, we can see that in this case, moving forward is moving us away from equilibrium. Climbing in energy requires an input of energy. Delta G would be positive. The reverse reaction would be moving us closer to equilibrium. Delta G would be negative. And so what we're going to do is just say, okay, we know that the standard free energy change is positive. So we need to find a place on this graph where moving forward is going to give us a positive delta G. And so that has to be to the right of our equilibrium constant. So here is a point that is greater than equilibrium constant. We will call this 1, and moving forward is positive endergonic. Therefore, the equilibrium constant must be less than 1 because it is over here to the left. Okay, let's look at another one. Here, the standard free energy change for the reaction of Q being converted to P is negative 375 kcals per mole. This means it is under standard conditions, 1 molar Q, 1 molar P. This reaction releases 375 kcals per mole. And we can determine if the equilibrium constant is less than 1, equal to 1, or greater than 1. Again, we're just going to plot this out. Free energy of the system on the y-axis, all possible ratios of P to Q on the x-axis. Our system is at lowest free energy when it is at equilibrium. Now, so far we haven't figured out what equilibrium is. But we know that for any value, any ratio of P to Q that is less than equilibrium, the forward reaction will be spontaneous, the reverse reaction will be non-spontaneous. Conversely, for any ratio of P to Q that is greater than the equilibrium constant, the forward reaction will be non-spontaneous, moving us away from equilibrium, climbing in energy. The reverse reaction would be spontaneous, moving us closer to equilibrium. And so we're told that the standard free energy change for this reaction is negative 375 kcals per mole. So if the standard free energy change of the forward reaction is negative, that must mean we are somewhere over here to the left of our equilibrium constant. And so, therefore, if the free energy change of the system, when the ratio of P to Q is 1, is negative, remember, this is the ratio of P to Q under standard conditions. If the free energy change is negative under standard conditions, that means moving forward is moving us closer to equilibrium. That means that equilibrium constant must be greater than 1. A third illustration. Suppose I told you that the conversion of C to D, a reversible reaction, has a standard free energy change of 0 kcals per mole. What can you tell me about the equilibrium constant? Well, we're going to do the exact same thing. Plot free energy of the system on the y-axis, equal all ratios of product to reactant, in this case D to C, on the x-axis. System is at lowest free energy when we are at equilibrium. Any ratio of D to C that is less than equilibrium constant will have a forward delta G that is negative, a reverse delta G that is positive. Any ratio of D to C that is greater than the equilibrium constant will have a forward delta G that is positive, reverse that is negative. Now, we're told that the standard free energy change for this reaction is 0. So where on this graph is the free energy 0? Well, the free energy change is going to be 0 at the lowest energy point of this reaction, when we are actually at equilibrium. It is at this minimum of this curve that the delta G for the forward and reverse reaction equals 0. Therefore, if the standard free energy change is equal to 0, and 0 is at the lowest free energy point on this graph, and equilibrium is the lowest free energy point on this graph, then the equilibrium constant must be 1. Because under standard conditions, our ratio of product to reactant is 1, and we are at equilibrium. So in these three examples, we can see that if the standard free energy change was greater than 0, I'll flip back here, if the standard free energy change was greater than 0, the equilibrium constant had to be less than 1. If the standard free energy change is less than 0, then the equilibrium constant must be greater than 1. And if the standard free energy change equals 0, then the equilibrium constant must be equal to 1. Now let's go in the reverse direction. Suppose you know only something about the equilibrium constant and you're asked to determine if the standard free energy change is positive, negative, or 0. Here's a reaction where we're converting ABC into DEF. We're told that the equilibrium constant is 0.3. What this means is when this reaction reaches equilibrium, the ratio of DEF to ABC will be 0.3. There will be 30% as much DEF as ABC. 3 DEFs for every 10 ABC molecules. So, our equilibrium constant is 0.3. What is the sign of the standard free energy change? Well, we just need to find now standard conditions on this x-axis. We know that the ratio of DEF to ABC under standard conditions is going to be 1 over 1. So 1 molar over 1 molar, which equals 1. And so we come over here to the right, and we see that we are at a higher free energy state than we would be if we were at equilibrium. And what we can see is moving forward would be moving us away from equilibrium. Therefore, the standard free energy change for the forward reaction is positive. Now suppose I told you that the equilibrium constant for the conversion of M into N is 1.3. What is the sign of the standard free energy change? Well, we do the exact same thing. We plot free energy on the y-axis by a ratio of product to reactant on the x-axis. We know that the system is at lowest energy when it is at equilibrium. In this case, the system is at lowest energy when the ratio of N to M is 1.3. So, what is the sign of the standard free energy change? Well, we need to find the ratio of product to reactant when we're under standard conditions. We know that standard conditions is 1 molar N over 1 molar M for a ratio of 1. So here we are. We're at 1, we come up, we're at a higher free energy than we would be if we were at equilibrium, but we can see that moving forward is moving us closer to equilibrium. And so in this case, the standard free energy change of the forward reaction will be negative. Finally, suppose I told you that the conversion of square into triangle, I got tired of letters, the conversion of square into triangle has an equilibrium constant of 1. What is the sign of the standard free energy change? Let's do the same thing. Plot free energy of the system on the y-axis, all possible ratios of product to reactant on the x-axis, and the system is at lowest free energy when it is at equilibrium, and in this case our equilibrium constant is equal to 1. Now we need to compare this value to our ratio of triangle to square under standard conditions. Well, under standard conditions we're going to have 1 molar triangle and 1 molar square, so 1 over 1 is 1. We're going to find that on this graph and we'll see, oh, it's right here. So, under standard conditions for this reaction specifically, we are at equilibrium. Therefore, since we're already at the lowest free energy state, there is no driving force for us to move forward or reverse. Our standard free energy change is 0 kcals per mole. Now, this is rare. Some students will mistakenly assume that standard conditions somehow means equilibrium. It usually does not. Only in very special cases is the equilibrium constant the same as what would be seen under standard conditions. And so maybe you've noticed a trend in what we have just looked at. This is a graph that is relating all possible equilibrium constants to all possible standard free energy changes. And you can see that there is a relationship. What we just saw on the previous example is that when the equilibrium constant is 1, the standard free energy change is 0. And what we saw in our other Examples is that when our equilibrium constant is less than 1, our standard free energy change is greater than 0. Whereas if our equilibrium constant is greater than 1, our standard free energy change is less than 0. And so given an equilibrium constant, you should be able to determine the sign of the standard free energy change. And given a standard free energy change value, you should be able to determine if the equilibrium constant is less than 1, equal to 1, or greater than 1. Now, these concepts, they're not extraordinarily difficult, but they may require some rehearsals. You might need to go back to the beginning of this video and work on it again. Maybe give yourself some new equilibrium constants and try to determine if the standard free energy change would be negative or positive, or 0. Same, give yourself some new standard free energy changes and see if you can determine whether or not the equilibrium constant is less than 1, equal to 1, or greater than 1. This is the kind of conceptual work that is doable, but requires a little bit of sweat and scratch paper. But you can do this.